Welcome to introductory workshop of NSCC National Supercomputing Center. We used to run physical workshops. However, due to various reasons, we are recording this session so users can watch the workshop whenever they want. Basically, there are two parts of this workshop. The first part is to discuss about the architecture, software, hardware, etc. And the second part, which is a separate video, walks you through hands-on, such as enrolling to NSCC, logging to the system, transferring the files, and doing some job submissions also as well. For now, let's jump into the agenda for this workshop. In this session, we will discuss about how NSCC was formed and what are the key goals of NSCC, followed by the basics of HPC. It's a brief on how the traditional supercomputers turned into the modern day HPC, aka high performance computing or high performance clusters. We would then discuss about Aspire 1, the high performance computing cluster, which consists of the brief architecture, hardware, the software, most importantly, the scheduler, followed by the user applications. Finally, we would like to give a brief on the containers that are supported in Aspire 1. Let me quickly introduce myself. My name is Srikanth Gumma. I'm part of Fujitsu Mini Services team. I have been managing this NSCC supercomputer from past 4 years. Before that, I have about 10 years of experience in different companies working with high performance computers for various roles, for example, for the pre-sales and installations, managing, maintaining the clusters, etc. Now, about National Supercomputing Center, NSCC, started with the vision of democratizing access to supercomputing. NSCC facilitates the necessary infrastructure to support research requirements throughout academic and industrial users, from students to scholars. The vision includes to support Singapore R&D initiatives, collaborate with industries for industrial research requirements, and to motivate and enhance Singapore research capabilities. Aspire 1 is the first petascale facility funded by NRF and collaborated with the founding stakeholders such as A Star, NTU, NUS, and SUTD. And we have more number of stakeholders joining the team to make NSCC much bigger. So we have high-speed networks to remote sites such as GIS, NTU, and NUS, where users connect through their local network to NSCC supercomputer. However, the user's login nodes are connected through InfiniBand network for high bandwidth. Moving forward, let's discuss about some basics of HPC. Now, the term HPC means high performance computing or high performance clusters. Traditionally, these are supercomputers. Supercomputers are meant for high throughput calculations, the basic concept of number crunching, data analytics, data parsing, etc. Well, the simple workflow would be input, process, output. Traditional supercomputers used to be proprietary architecture, proprietary operating system, etc. So that these are all very expensive, not only in terms of money, but also in terms of code, moving from one system to another system, moving from one architecture to another architecture. it's going to be too expensive. So, once the open platforms emerged, such as x86 based architecture and modern Linux evolution, gave a chance to many researchers to start a lower cost HPC systems. It's not necessarily stuck with one architecture. The new architecture are not only powerful but also smaller in size and less expensive. FLOPS, floating point operations per second, which is typical measurement of a supercomputer size in HPC clusters. So the modern day supercomputers can be made with a cluster of more than one PC, which includes but not limited to desktops, workstations, servers, also the mobile phones. The process of HPC workflow is very simple: input, process, output. If you are new to HPC world, some of the concepts might be used interchangeably, but the terms such as virtualization, cloud computing are not part of HPC. HPC does not host web server, nor databases, or any other enterprise applications such as SAP. Let's see an example of a car crash simulation in this slide. We can see the car mesh which was created in a desktop, and then the researcher prepares the necessary input files, transfers them to HPC. The researcher then submit a job through HPC system for crash analysis, which is usually a compute intensive job. Finally, the results are captured and viewed through visualization software. Basically, the concept of HPC is to maximize the resource utilization by using more than one process. It could be single machine parallelization via SMP process or via multi-node using high-speed interconnectivity such as InfiniBand, or run small single process jobs simultaneously through job arrays. I'm sorry, some of this concept might be pretty new to some of the users. However, it is very important to know or understand these concepts to achieve usage of high performance computing systems. Let's jump into the Aspire 1 architecture. Whenever I discuss about HPC, my tendency is to discuss about the HPC stack, the stack which is used to build the entire supercomputer. At the lowest level in this slide, we can see there were hardware where the servers are based on Fujitsu x86 Intel CPU based servers with a few GPU servers installed with Tesla K40 for hybrid computing. And we have DDN hardware for the storage. Next up, the interconnectivity is through Mellanox InfiniBand EDR, which provides a bandwidth of 100 Gbps. The operating system platform for Aspire 1 is based on Red Hat 6 and CentOS 7. By the way, we don't have any other operating systems like Ubuntu or Microsoft. We have the hardware storage based on DDN. However, to use the storage, we need to have a file system. The most popular GPFS and Lustre, both the file systems are being used in NSCC for home and scratch respectively. So far, we have discussed about the base layers of cluster. Now comes the most powerful and useful parts for the users. Though other layers are important to know, but most of the time users would be interacting with the upper layers such as compilers, libraries, applications, besides the scheduler. We have Intel compiler suite license, as well as we have GNU compiler stack as well, which are discussed in bit detail in the later sections of the same video recording. PBS Pro is a commercial job scheduler chosen to be used in Aspire 1 cluster, whereas we have license for debugging and profiling tools from Alinea or ARM tools. To know more details about ARM tools, you can head to the portal help.nscc.sg, navigate through user guides, and find out the user guides on ARM tools. We have so many versions of software, so many flavors of compilers and tools. We should have a mechanism to choose them or operate them dynamically. Here comes the most important or powerful tool, which is environment modules. We use the load to particular environment or unload them whenever it's necessary. So we do have several open source applications. However, commercial licenses are not purchased site wise. So if any users have a commercial applications requirement, we welcome them to bring their license to NSCC and we can help them to host for their applications to run. Here we can see the complete architecture of Aspire 1. At the lowest segment, we can see dedicated login nodes placed for NUS and NTU. Well, A star have their own dedicated servers which are located in NSCC itself. However, A star users are connecting directly to the servers which are located within the same network segment of A star. Therefore, they don't need a high speed connectivity connecting from NSCC systems to A star login nodes. However, for other users such as NUS and NTU, they are connecting to their remote login nodes, which the login nodes are placed in their sites. However, there is a high speed bandwidth link which is connected between NUS site to NSCC, NTU site to NSCC, so that users whenever they are login they just log into their local system through their local network. So the users doesn't require to log in a specialized VPN to connect to NSCC. For all other users including SUTD and the direct users must connect to NSCC VPN when they are connecting from outside. SUTD doesn't have a dedicated InfiniBand link. However, there is a leased line which is connected between NSCC site to SUTD. Here there is a small cache. So when SUTD users are not connecting to through their SUTD network, they must connect to NSCC VPN. For all other users, they should connect, I mean, for A star, NUS, and NTU, they must connect back to their organization VPN. For example, NUS users connect to NUS VPN, A star users connect to A star VPN, NTU users connect to NTU VPN, and they can access NSCC login nodes remotely. One particular point I wanted to highlight in this architecture, we can see there is a GIS FAT node. It's a special requirement from GIS. This FAT node is configured with high memory, which is 1 terabytes of memory, and there is a sequencing machine and the storage connected directly through GIS FAT node, where the sequencing machine puts the data directly to NSCC storage. So such kind of specialized configurations are possible, and we welcome to incorporate such changes in NSCC. Hardware. As we saw in the stack, there is a starting point of hardware. Let's see some of the details in the hardware. NSCC has a CPU based compute. with a standard 4 GB per core config. Some nodes with high memory configurations, accelerator nodes, DGX machines, all connected through high throughput InfiniBand 100 Gbps network. The overall throughput of Aspire 1 cluster is 1 petaflop, an exception being the AI servers or DGX servers. Without AI or DGX servers, NSCC is achieving 1 petaflop, which consists of 1160 compute nodes. As I said earlier, each compute is with 24 cores, dual socket, and memory of 128 GB per node physically. However, there is a usable capacity is only 96 GB because we don't have hard disks or physical hard disks in compute nodes. Therefore, we have to create a virtual disk which uses some part of RAM and creates a virtual disk for hosting the operating system. There are 9 large memory nodes configured with 1 TB, which are 4 systems, another 4 with 2 TB, another 1 node with 6 TB configurations. There is 13 petabytes of storage, including IME, Scratch, home or projects, and archive. IME, being a burst buffer, provides 500 Gbps throughput, and 200 Gbps throughput is achieved through Lustre, 100 Gbps throughput with home or project file system. The archive file system is very slow. It's about 100 gigabytes per hour configuration, wherein the archive storage is specifically used by the administrators to archive projects data which are older than 30 days after expiry. There are 128 GPU nodes configured with similar CPU configurations, exception being one Tesla card K40 installed in each of the node. To be precise, we have 24 cores per server, 128 GB of memory, and 1x Tesla K40 card installed per server. A common component across all these nodes is they are diskless, and all the nodes are liquid cooled. We have two visualization servers which are configured with the two times NVIDIA Quadro K4200 GPU cards for high-end visualization. A recent addition to NSCC or Aspire is Aspire 1 Plus, which is configured for set of users specifically for climate research. Aspire 1 Plus also includes a HTC system, which is high throughput computing, basically small size of jobs and many jobs are being assigned where the users doesn't have a direct access to the system. This is being administrators are choosing the jobs which need to be moved to this HTC system. So users cannot move the jobs to HTC queue, nor they can view any details of HTC jobs, or they cannot kill the jobs also as well. If they need anything to be done with the HTC system, they must approach administrator to kill or terminate the jobs. Moving forward, let's see a little depth on the configuration of hardware components. So now first up here we have STD and LMN nodes. The configuration is same for all STD nodes. Therefore, the name STD or standard compute nodes are built on Fujitsu hardware. The model used for the compute nodes is CX2550M1 servers, each with 12 cores and dual sockets, making 24 cores in total per server. Though there is 128 GB of physical memory available, due to the nature of diskless configuration, some part of memory is being used for virtual disk. As I said earlier, Therefore, the usable memory is only 96 GB per server. Coming to the large memory nodes, the host name starts with large mem or LMN. We have total 9 RX 4770 M2 servers with 24 or 48 CPUs per server configured. As mentioned earlier, these servers are with 4 1 TB configurations, 4 2 TB configurations, and 1 6 TB configuration. All the STD and GPU nodes are liquid cooled servers to ensure lower carbon footprint. GPU and visualization setup consists of 128 GPU nodes built on Fujitsu CX2570 M1 servers, and the configuration is pretty much similar to STD nodes. Two visualization nodes, which are 2x NVIDIA Quadro K4200 cards, are used for remote visualization. In the practice session, we can start visualization job and see how it works. Especially there were application called display manager, which we would be using to do a remote visualization. For example, a paraview or any other high-end visualization application. In the DGX setup, we have total 6 DGX servers. Each is configured with 40 CPUs and 8 V100 GPUs. We have 512 GB of memory per server. All the infrastructure is connected through Mellanox 100 Gbps network. Storage. As I said earlier, we have 4 different layers of file systems. The first one is the accelerator or burst buffer, DDN's infinite memory engine, which provides the bandwidth of 500 Gbps, which is used for parallel I/O to achieve such high bandwidth. Unless the applications has a demands on such high bandwidth, we do not recommend to use IME for normal applications. Scratch file system is meant for temporary storage with a higher throughput of 210 gigabytes per second. However, files stored in Scratch are not to be retained for a longer time. We have a 30 days purge policy implemented to clean up files older than 30 days. GPFS file system is being used for 3 different file systems. One is home directory, second is the projects, and third one is for the archive as well. The slowest file system is being archive file system upon completion of projects, and if the projects are not being extended, such project files are being archived by our administrators in the archive storage for a period of time before it gets purged completely. So by default, users doesn't have a direct access to the archive file system. Cluster software. In this stack, we move upper levels. We can see the operating system RHEL or CentOS based operating system. The login nodes are being set up with Red Hat RHEL 6.10, and all compute nodes are set up with CentOS 6.10 operating system. Though the flavor is same, different operating systems for different purposes. Some of the stacks we have make a note here are GCC 4.9.3, which is supported version, and Intel Parallel Studio, which comes with Intel C, C++, MPI, and MKL. We have wide variety of support from open source libraries such as BLAS, LAPACK, FFTW, and we also have license to use MKL platform. ARM tools for debugging and profiling. There might be another workshop conducted for complete ARM tools However, there is a user guide located in the portal as I said earlier. You can head over to help.nssc.se and navigate to user guides and look for ARM tools. For GPU platform, we have CUDA 10.1 installed, and that is the not the latest version but one version previous to the one. Let's discuss a bit about PBS Professional. So we have three components in job scheduler, that is job scheduler, compute manager or display manager, and AM for project management. The process flow of PBS job. In this workflow, we may see some terminology which are the terms that are not significant for the users, but the flow of the job is very important. At first, let's look at the job flow. We can see the step here one by one. At first, a user submits a job and PBS receives the request and returns with a job ID. The job ID is the identifier for the job lifecycle. The job lifecycle is from the job submitted until the job is finished plus 1 hour of history time. Based on the requested resources through the job submission command or script, PBS scheduler requests the resources from PBS server. In the next step, PBS scheduler sorts all the resources and jobs. Next, PBS scheduler informs PBS server on resources that are available where the job can run. For example, if the job is requesting for 12 CPUs and 48 GB of memory, the scheduler finds available nodes which matches 12 CPUs and 48 GB of memory and reports it to the PBS server. Now the PBS server sends the job to the server where the node is allocated to the job. There is a component called PBS MOM, Machine Oriented Mini Server, which actually keeps track of the node where the job is running and responsible for executing the job. While PBS MOM also does the reporting periodically to PBS server. Last but one step is to copy back the error and output files once the job is finished. Finally, the user gets notified in case if there is a notification configured. These steps are very important to understand because once the job is submitted until the various stages it has to go through, so the job state depends on step where the job is in. When submitted, the job starts with a queue state and remains in the same until the job gets resources allocated and pushed to the compute node for execution. Once execution begins, the job state changes to R. While copying files back, it changes state to E. Finally, once the job is finished, it shows as F, finished. Sometimes we might see some other states, so those states are different levels of job state. For example, hold state, H state, which occurs sometimes in case if there is a job failure and repeated attempts and if the job cannot go through. So, and another case is if the job is submitted through a job dependency, job will be on hold state. If the user has a specific requirement and puts a job on hold state, then also it shows in H state. So the job history is maintained for 1 hour after completion of the job. In case if the job is completed and 1 hour is finished, the history of the job is no more maintained. In case if you wanted to know about the job, we must look through the output and error files of the job. Let's talk about the queues in NSCC. We have two different types of queues. One is external, another one is internal queues or hidden queues, non-accessible to the users. So we have several queues configured to handle different workloads. In the slides, We can see queues listed as listing all queue is not so practical, but to give an idea of how the system is set up. We have a classification of external and internal queues. Here we see some of the external queues named large mem, normal and GPU broadly for the users to understanding. So as the name suggested, large mem queue is for the jobs which needs high memory than the standard compute nodes, which means more than 96 GB of memory. Second queue, what we see here is the normal queue, which is the standard compute nodes, configurations of up to 24 cores per server and 1 CPU until 3000 CPUs or cores. The third queue, what we see here is the GPU queue, which is meant for K40 GPUs only. The internal queues are not accessible for the users directly, means users cannot submit job directly to these queues. However, these queues are configured to have different priorities based on the resources requested. For example, it is totally unfair for a job to wait for more than job requires one core and 1 hour to wait for longer. Therefore, such jobs are given a higher priority to go through the dev queue. Similarly, we have a standard limitation of maximum 24 hours for any given job. Exception for a single node job can request more than 24 hours and less than 120 hours. Such job will land in long queue. These are typically having lower priority and lands in long queue. We have a user guide, NSCC Job Scheduler Quick Start Guide from the portal help.nscc.sg. Navigate through user guides, where we have several examples of job submissions which are detailed with the examples. We have separate queues for DGX. So the DGX queues are slightly different. So when the users wanted to submit a job, they can submit to DGX or DGX-dev queues. So there are different workloads, and based on the workloads we segregate into different internal queues in DGX setup also as well. So for more details on DGX queues, you may head over to https help.nscc.sg user guides AI system quick start guide. The next component of Altair AM Shoot is AM or account management. We often refer as projects in NSCC. Basically, AM is allocation management system where users are pre-allocated with certain number of CPU hours either for personal execution or through project allocation. For stakeholders such as A star, NUS, NTU, SUTD, there is a one-time allocation of 100,000 CPU hours in their personal accounts. This allocation is fixed for lifetime. So if the CPU's hours is exhausted in personal project, there is no way we do any further deposits. Alternatively, users can raise a request through the project portal once in every 6 months when the announcement is made for the call for projects. Then there can be deposits made in the projects based on the approval. As a side note, for non-stakeholders, users must approach our business development team through bizdev at nscc.sg for project creations and allocations into the projects as there are commercials involved. For stakeholders users such as NUS, NTU, NUS, A star, SUDD, they can submit the project request through project portal. There are several software and applications which are installed in NSCC Aspire 1 system available through modules. So It is not practical to go through each and every software and give a detail on the software. You can visit help.nssc.sg for some of the softwares list. However, this list could be a little outdated. You may visit module avail command to see all the available modules or available software. Um, Environment modules plays a important role to maintain several versions of softwares and tools and applications in the system. It's very simple tool, and with very few commands to know, we can create one module per tool or library or applications. I discussed about environment modules more detail in the practical session, as it's more on hands-on than theory part. However, just to remember, environment modules are written in TCL language and only sets environment variables such as path, LD library path, or aliases, etc., or any other environment variables for that matter. The advantage is, the advantage with the environment modules is any application or library environment can be loaded or unloaded dynamically without login or log out of the system, or without changing the content in .bashrc file. In NSCC, we do support containers, more popularly known as DevOps. However, our containers are limited to using applications that are not natively supported on the host OS. We do not do container development or host applications such as web server or DB servers with the containers. But these containers are only used for application executions, specifically HPC application execution. Currently, Aspire 1 only supports Singularity containers, whereas DGX servers we have DGXQ support both Singularity and Docker. We have several containers already available in /app/singularity/images directory, which can be used for normal GPU queues. Due to host operating limitations, either Ubuntu 16 or CentOS 7 based containers are only supported in the container. Please note that this is only for STD or GPU nodes. For DGX setup, it's completely different. DGX containers support more latest version of containers. However, DGX support is only restricted for Aspire 1, AI research. In this slide, we can see some of the examples. However, these examples are again repeated in the hands-on session. The usage is pretty simple. The job submission script load only Singularity module and invoke the respective Singularity image to Singularity exec command. Docker containers are only supported in DGX system. Login nodes can show the available Docker images. However, login nodes does not or cannot execute any Docker commands. For more information, please visit AI System Quick Start Guide from user guides in help.nssc.sg portal. Before we conclude, here is where we are located. For all Q&A, please contact help@nscc.sg. Some of the useful URLs and emails are listed here to reach our technical help. Thank you for watching this session. Please feel free to contact us at help@nscc.sg or call us on the phone number given in this slide.